The nearest star to Earth is called Proxima Centauri. It is 4.24 light-years away. That is the closest star, and yet it is so distant that even Voyager 1, moving at 17 kilometers per second, would take about 73,000 years to reach it. In 2016, astronomers announced a discovery that instantly became one of the most discussed in the history of exoplanet science. A planet was found orbiting Proxima Centauri, a planet roughly Earth-sized, on an orbit in the star's habitable zone, where temperatures theoretically allow liquid water to exist on the surface. Proxima b, the nearest potentially habitable exoplanet to us. The reaction was predictable: excitement, headlines about a second Earth, conversations about how we might someday get there, plans for interstellar missions, dreams that life in the universe is common, and the nearest example is literally on our doorstep. All of this is understandable. The discovery is genuinely significant. But between potentially habitable zone and actually habitable, there is a gulf. And between actually habitable and habitable for humans, there is another gulf. Tonight, we are going to look at Proxima b honestly, not as a dream planet, but as a specific physical place with specific conditions. We will examine each of the factors that make this planet potentially habitable, and each of the factors that make it potentially lethal. If the night is long, stay. Let us begin with Proxima Centauri itself, because to understand the planet, you first need to understand its star. And Proxima is not the Sun. Proxima Centauri is a red dwarf, a star of spectral class M5.5 VE. This means the following. Mass, about 12% of the Sun's mass. It is 8 times lighter than our star. Size, about 15% of the Sun's radius, roughly 7 times smaller. Surface temperature, about 3050 Kelvin versus 5778 Kelvin for the Sun. Proxima is nearly twice as cool. Luminosity, about 0.15% of the Sun's luminosity. Yes, 1.5 thousandths of our Sun's output. This is a very dim star. For a planet to receive the same amount of heat as Earth receives from the Sun, it must be located significantly closer to its star than Earth is to the Sun. In Proxima's case, the habitable zone begins at roughly 0.04 to 0.08 astronomical units from the star. For comparison, Mercury is at 0.39 astronomical units from the Sun. Proxima b is at 0.0485 astronomical units from Proxima Centauri. That is roughly 8 times closer to its star than Mercury is to the Sun. Orbital period, about 11.2 Earth days. 1 year on Proxima b lasts just over 11 Earth days. This already paints a certain picture, a planet very close to its star, and such proximity has consequences. Let us now talk about tidal locking, the first and perhaps most fundamental factor determining conditions on Proxima b. When a planet is very close to its star, tidal forces from that star slow its rotation. This is the same physics that caused the Moon to always face one side toward Earth. The Moon is tidally locked to Earth. It rotates around its own axis with exactly the same period as around Earth. For Proxima b, with an orbital period of 11.2 days at a distance of 0.0485 astronomical units from its star, tidal locking is essentially inevitable. The time to reach synchronous rotation for a body at this distance from this kind of star is significantly less than the age of the system. Unless something prevented this locking, a strong initial rotation rate, a large moon, an orbital resonance, Proxima b is almost certainly tidally locked now. What does this mean physically? One side of the planet, the day side, always faces Proxima Centauri. Always. Eternal day. The other side, the night side, always points away from the star. Always. Eternal night. This is not just a strange astronomical feature. It is a fundamentally different thermal regime for the planet than Earth's. On Earth, solar heat is distributed around the planet through its 24-hour rotation. Every 24 hours, each point on the surface transitions from day to night and back. This creates a relatively uniform temperature regime. No point is continuously heated, and no point cools forever. On a tidally locked Proxima b, the day side receives continuous heating. The night side never receives direct stellar radiation. What happens to temperatures under these conditions? Without an atmosphere, the day side would heat to several hundred degrees Celsius. The night side would cool to roughly -100 degrees and below. The temperature difference between sides, several hundred degrees. With an atmosphere, the situation depends on the properties of that atmosphere. A sufficiently dense atmosphere could transport heat from the day side to the night side through atmospheric circulation, the way winds on Earth transport heat from the equator toward the poles. This would moderate the extreme temperatures on both sides, but complete equalization would not occur. Modelling shows that even with a dense atmosphere, the day side is significantly warmer than the night side. Somewhere on the boundary between them, the so-called terminator zone, conditions could be most moderate. The terminator zone, a narrow band along the boundary of eternal day and eternal night, is the hypothetically most habitable part of a tidally locked planet. There is no continuous day and no eternal night. There, Proxima Centauri always stands low on the horizon, like a permanent sunset or sunrise. But the terminator zone is narrow, and conditions there depend on the presence and properties of an atmosphere we know nothing about. Let us now talk about radiation, because this is probably the most lethal aspect of life near Proxima Centauri. Red dwarfs, as a class, are exceptionally magnetically active, especially in youth, but throughout most of their lives. Proxima Centauri is no exception. Proxima is an extremely active flare star. Stellar flares are sudden bursts of energy from the star's surface caused by reconnection of magnetic field lines. On the Sun, flares occur periodically and can be very powerful, but even the largest solar flares create only temporary elevated radiation at Earth. Proxima flares incomparably more often and incomparably more powerfully relative to its baseline luminosity. In May 2019, the Hubble Space Telescope detected a flare at Proxima of such power that it was thousands of times brighter than the largest solar flares known for the Sun. This was a flare sometimes called a superflare, an event that released an enormous amount of ultraviolet radiation and X-rays. Superflares at Proxima are not rare. They occur several times per year by some estimates. What does this mean for Proxima b? The planet is at 0.0485 astronomical units from Proxima, 8 times closer to its star than Mercury is to the Sun. During a superflare, the intensity of ultraviolet and X-ray radiation reaching the planet is hundreds or thousands of times the normal level. For the atmosphere, intense ultraviolet radiation photodissociates molecules in the upper atmosphere, destroys ozone, dissociates water molecules, creates highly reactive radicals. These are atmospheric destruction processes that work against maintaining a stable atmosphere. For a possible biosphere, ultraviolet doses during a superflare would be many times the lethal dose for most Earth organisms without protection. in the absence of a powerful ozone shield, which is itself a problem as we will discuss, the surface during a flare would be exposed to DNA-destroying radiation doses. And between flares, the baseline radiation dose on Proxima b is significantly higher than on Earth. Because of the planet's proximity to its star, even normal ultraviolet radiation, though proportionally less than the Sun's because of the cooler star, reaches the planet with much greater intensity simply due to the small distance. Additionally, stellar flares are accompanied by coronal mass ejections, clouds of charged particles emitted from the star. On Earth, the magnetic field deflects most of these particles, protecting the atmosphere and surface. Does Proxima b have a magnetic field? We do not know. The presence and strength of a magnetic field depends on many factors: the planet's size, the rotation speed of the iron core, the presence of a liquid core. A tidally locked planet rotates slowly, and slow rotation is unfavorable for generating a powerful magnetic field through the dynamo effect. If Proxima b lacks or nearly lacks a magnetic field, the charged particles of coronal mass ejections will directly interact with its atmosphere. This accelerates atmospheric erosion. Ionized gas in the upper atmosphere is captured and carried away by the stellar wind. This is exactly what happened to Mars. Mars lost its magnetic field about 4 billion years ago. After that, the solar wind gradually stripped the Martian atmosphere, and today the surface pressure on Mars is less than 1% of Earth's. If a similar process occurred or is occurring on Proxima b, with a significantly more active star, then the planet may have lost most of its primary atmosphere over the system's lifetime. Let us now talk about water, about what the question of liquid water on Proxima b actually looks like under honest examination. The habitable zone is a concept developed for planets that receive enough stellar radiation that liquid water could theoretically exist on their surfaces. It does not mean water is there. It does not mean there is an atmosphere. It does not mean the planet is habitable. It means only that if the planet has a surface and an Earth-like atmosphere, the temperature could allow liquid water. For Proxima b, the habitable zone is just one of many conditions, and even this condition is called into question by several factors. First, water must be there originally. Planets form from protoplanetary disk material. The relatively small mass of Proxima Centauri and its weak luminosity mean the snow line, the boundary beyond which water condenses into ice in the protoplanetary disk, was closer to the star than for the Sun. This potentially allowed the planet to form with some water. But Proxima b's distance from its star is so small that during the formation period, when the young star was brighter, the planet may have been outside the habitable zone. Young red dwarfs go through a period of high luminosity in the first hundreds of millions of years of their lives. During this period, Proxima b may have received significantly more radiation than now, potentially triggering a massive greenhouse effect and evaporation of water into the atmosphere. This phenomenon is called the moist greenhouse effect, or runaway greenhouse effect, when intense radiation causes large quantities of water to evaporate, which then dissociates under ultraviolet in the upper atmosphere, and hydrogen escapes into space. Earth avoided this fate because the Sun was dim enough in its youth. Proxima may have been bright enough in its early stages to trigger this on its planet. If the runaway greenhouse effect occurred, Proxima b may have lost most of its primary water in the first hundreds of millions of years. The planet we see today could be dry, or significantly less water-rich than Earth. Second, even if water survived, its distribution on a tidally locked planet would be extremely non-uniform. On the night side, ice, possibly enormous ice caps or entire ice hemispheres. On the day side, possibly liquid water if the atmosphere is dense enough. But if the night side is cold enough, it can act as a water trap. Water vapour transported by atmospheric circulation from dayside to nightside condenses and freezes. Water gradually moves from the dayside to the nightside until the dayside is completely dry and the nightside is buried under ice. This is called the cold trap, and it is a serious problem for tidally locked planets in habitable zones. Let us now talk about the stellar wind of Proxima Centauri and the specific type of radiation impact unique to planets near active red dwarfs. Proxima's stellar wind is significantly more powerful compared to the solar wind at Earth, not because Proxima produces a greater flux of particles in absolute numbers, it is a less powerful star, but because Proxima b is so close to its star that the wind density at the planet is much higher. Stellar wind density decreases proportionally to the square of the distance. At 0.0485 astronomical units, 8 times smaller than Mercury's distance from the Sun, the wind density is roughly 64 times higher than it would be at Mercury from the solar wind. Additionally, Proxima generates a more intense wind than the Sun relative to its size. Result? The stellar wind pressure on Proxima b's atmosphere is incomparably higher than solar wind pressure on Earth's atmosphere. If Proxima b has no strong magnetic field, this pressure directly acts on the upper atmospheric layers. Wind particles ionize atmospheric gas and carry it off into space. Estimates of the rate of atmospheric erosion of Proxima b from stellar wind without a magnetic field give alarming numbers. Some models suggest that over the system's lifetime, about 5 billion years given Proxima's estimated age of 4.85 billion years, the planet could have lost several times the Earth equivalent of atmosphere. This does not mean there is no atmosphere. Volcanic outgassing and other geological processes can replenish the atmosphere, but it means that maintaining an Earth-like atmosphere on Proxima b requires active replenishment from geological sources to compensate for losses from stellar wind. Is Proxima b geologically active? We do not know. Tidal locking means that much of the rotational energy was dissipated, possibly this maintained geothermal activity in the early stages. But now, with established synchronous rotation, there is no additional tidal heating. Let us now talk about what light would be like on Proxima b, because this is one of the least obvious but most radical aspects of this world. Proxima Centauri emits predominantly in the red and near-infrared range. This directly follows from its surface temperature of 3050 Kelvin. Wien's displacement law says that the emission maximum of a body at 3050 Kelvin falls at a wavelength of about 950 nanometers, the near-infrared range, beyond the human visible spectrum. This means most of Proxima Centauri's energy falls on wavelengths the human eye barely perceives. In the visible range, the range we can see, Proxima emits significantly less than the Sun. On Proxima b's surface, assuming an atmosphere exists and has a reasonable composition, the dayside would be illuminated by light perceived as dim reddish or orange, not the bright white or yellow of a sunny day on Earth. Something more resembling deep twilight with a reddish tint. The star in the sky, assuming the atmosphere scatters enough light, would appear significantly larger in angular diameter than our Sun from Earth. At a distance of 0.0485 astronomical units, and with Proxima's diameter about 15% of the Sun's, the angular diameter of Proxima from the planet's surface is roughly 3 times larger than the angular diameter of the Sun from Earth. The star would occupy roughly 9 times more area of sky. An enormous dark red star standing motionless in the sky of the dayside, never moving, never setting, never rising, just there. What does this mean for photosynthesis if life exists on Proxima b? Earth plants are adapted to sunlight, to the spectrum our sun produces. Chlorophyll absorbs primarily red and blue light. Green light is reflected, which is why plants look green. On Proxima b, most available light falls in the near-infrared range. If photosynthesizing life exists there, it would need to be adapted to absorbing these wavelengths. Theoretical work suggests that pigments absorbing near-infrared light would be black or dark purple, maximally absorbing the available light rather than reflecting it as Earth plants reflect green. A hypothetical biosphere on Proxima b could look completely different from Earth's, not green but dark, almost black, to maximally utilize the available infrared light. Let us now talk about the specific calculation that helps understand the scale of the radiation problem on Proxima b, about exactly how much ultraviolet radiation the surface receives compared to Earth. On Earth, the atmosphere and magnetosphere protect the surface from most dangerous ultraviolet radiation. The ozone layer absorbs almost all UVC, wavelengths 100 to 280 nanometers, the most biologically dangerous range, and most UVB, 280 to 315 nanometers, moderately dangerous. UVA, 315 to 400 nanometers, mostly passes through the atmosphere. Under normal Earth conditions, the surface receives primarily UVA, with a small admixture of UVB. UVC barely reaches the surface. What happens on Proxima b? During stellar flares, even moderate ones, red dwarfs emit a disproportionately large amount of UV and X-rays relative to their normal luminosity. The difference between baseline UV and the level during a flare is much greater for red dwarfs than for Sun-like stars. The superflare detected at Proxima in 2019 increased the star's total luminosity roughly 14,000 times at peak. Most of the additional energy fell precisely in the ultraviolet and X-ray ranges. Calculations show that during such a superflare, Proxima b's surface, without an atmosphere, would receive a UVC dose roughly 65,000 times higher than Earth's surface under normal conditions. This is not merely lethal to most known organisms. It approaches doses at which organic molecules themselves are destroyed. Even if Proxima b has an atmosphere, the question is how transparent that atmosphere might be to UV. Earth's ozone layer forms from molecular oxygen, O2, through photochemical reactions triggered by UV. To form ozone, you need oxygen. For oxygen, in significant quantities, you need life. On Earth, oxygen in the atmosphere is primarily a biological product, produced by photosynthesis. If Proxima b has no biological production of oxygen, there is no ozone layer in the Earth sense, an atmosphere of CO2 and N2 without significant O2 and O3 is relatively transparent to UV. This creates a paradox. Life is needed to produce oxygen. Oxygen is needed for ozone. Ozone is needed to protect life from ultraviolet. How does life appear and survive long enough to produce sufficient oxygen to protect itself? On early Earth, the same problem. The first 2 billion years, life on Earth existed without significant oxygen in the atmosphere, and therefore without an ozone layer. It was predominantly underwater. Water absorbs dangerous UV. Or lived in rock crevices, or developed its own pigments for protection. This is the same path that potential life on Proxima b would have to take, only under conditions of significantly more intense stellar activity. Let us now talk about the orbital resonance alternative to complete tidal locking, about the 3:2 resonance, and why it matters for understanding Proxima b. Mercury, the planet closest to the Sun in our system, was long believed to be tidally locked. For a long time it was thought Mercury showed one face to the Sun, just as the Moon shows one face to Earth. This seemed inevitable given its proximity to the Sun. When radar observations in the 1960s allowed precise measurement of Mercury's rotation period, it turned out Mercury is in a 3:2 resonance. For every 2 orbits around the Sun, Mercury completes 3 full rotations around its own axis. This is not complete tidal locking, 1:1. This is a more complex orbital resonance. In a 3:2 resonance, Mercury has a very slow day. 1 Mercurian day equals roughly 176 Earth days. But different parts of the surface do take turns facing the Sun. There is no permanent dayside and nightside in the absolute sense. Could Proxima b have ended up in an analogous 3:2 resonance rather than complete tidal locking? Theoretically, yes. The 3:2 orbital resonance is a stable state under certain conditions, specifically with orbital eccentricity. If Proxima b's orbit is slightly eccentric, not perfectly circular, the 3:2 resonance is a more probable final state than complete 1:1 tidal locking. What would this change? In a 3:2 resonance, all sides of the planet periodically face the star. There is no permanent dayside and permanent nightside. The thermal contrast between hemispheres is significantly smaller. All regions of the planet alternately heat and cool. This significantly improves the habitability situation. Water does not freeze permanently on the night side. Temperatures are more uniform, no extreme thermal stress. However, the rotation period in a 3:2 resonance with an orbital period of 11.2 days would be about 7.5 days. This is still slow rotation, nearly 8 times slower than Earth. Slow rotation is unfavorable for the magnetic dynamo, and the radiation protection problem remains. We do not know in which rotation state Proxima b actually is. This is one of the key questions future observations need to answer. Let us now talk about the comparison to the most extreme natural environments on Earth, because this helps calibrate what range of life might be possible on Proxima b. The most extreme natural environments on Earth, the dry valleys of Antarctica. One of the driest and coldest places on Earth, average temperature around -20 degrees Celsius, nearly zero humidity. Despite this, life is found here. Crypto-endendolithic communities, microorganisms living in the pores of rocks a few millimeters below the surface. There they are protected from ultraviolet, receive a small amount of diffuse light through semi-transparent mineral grains, and survive on minimal liquid water formed through rock warming. Acidic hot springs with pH around 0 to 1, practically concentrated sulfuric acid, temperature up to 100 degrees Celsius. Nevertheless, thermophilic, acidophilic bacteria and archaea thrive in such conditions. Deep-sea hydrothermal vents, complete darkness, pressures of hundreds of atmospheres, temperatures up to 400 degrees at the vent, though organisms live some distance away where temperatures are more moderate. Chemosynthetic ecosystems exist entirely without sunlight. No single one of these environments is a complete analogue to conditions on Proxima b, but each demonstrates that life is found where we did not expect to find it, and that the range of its adaptive capabilities extends beyond our initial expectations. The fundamental difference between Proxima b and all these environments, the intensity and unpredictability of radiation events. A superflare is not a constant condition. It is a sudden and brief event, tens of thousands of times exceeding the normal level. Biology on Earth is adapted to constant stressors. Adaptation to rare but catastrophic events requires different mechanisms, possibly cryptobiosis, the ability to completely halt metabolism under extreme conditions, or exceptionally rapid repair after an event. Tardigrades, microscopic multicellular organisms, are capable of cryptobiosis. In a state of anhydrobiosis, they survive radiation doses of 570,000 rads and temperatures from -272 to +150 Celsius. They are the most radiation-resistant known multicellular organisms. Even tardigrades would not survive Proxima b's surface during a superflare without additional protection. But they show how far evolution can go in adapting to extreme conditions. Let us now talk about the specific scientific debate that is most active regarding Proxima b, about whether the discovery itself is reliable and what exactly was found. Proxima b was detected through the radial velocity method, by the periodic wobble of the star caused by the gravitational pull of the planet. This is the same technique that discovered 51 Pegasi b in 1995, the first exoplanet around a Sun-like star. The discoverers, Guillem Anglada Escudé and his team, published the result in Nature in 2016. The signal showed periodicity of about 11.2 days and an amplitude corresponding to an object with a minimum mass of about 1.27 Earth masses. Immediately after publication, doubts arose. The main problem, Proxima Centauri is an active star. Stellar activity, spots, brightness variations, convective motions, create signals in radial velocities that can mimic a planetary signal. A group of authors in 2020 proposed that the Proxima b signal might be an artifact of stellar activity rather than a real planet. Their analysis showed the signal could arise from an annual stellar activity cycle interacting with the specific rhythm of observations. Subsequent work produced contradictory results. A number of independent analyses confirmed the signal is real and most plausibly explained by a planet. Others continued pointing to possible stellar artifacts. As of today, Proxima b is considered a confirmed planet by most of the astronomical community, but with the understanding that the confidence level is somewhat lower than for transit planets or planets detected by multiple independent methods. The espresso spectrograph, the world's most precise radial velocity instrument, confirmed the planet's signal in 2020. This is the most important independent confirmation to date. But this context matters. We are talking about a world that in some sense is not yet definitively confirmed. Let us now talk about what we actually want to measure about Proxima b and how this will change our understanding about the observational priorities for the next decade. Priority 1. The presence of an atmosphere. Any evidence of an atmosphere, even indirect, immediately changes the picture. Spectral signatures of CO2, H2O, N2 or other components. Refraction of starlight at limb observations. Thermal emission consistent with an atmospheric greenhouse effect. Priority 2. Atmospheric composition. If an atmosphere is found, its composition. Earth-like with O2 and N2, Venus-like with CO2, something fundamentally different. The presence of O2 combined with other biosignatures would be exceptionally exciting. Priority 3. The presence of water. Spectral signatures of liquid water or water vapor. This speaks to temperature conditions permitting liquid water. Priority 4. The magnetic field. Indirect signatures of a magnetic field, auroras analogous to Earth's, interaction with the stellar wind. A powerful magnetic field makes habitability significantly more probable. The Extremely Large Telescope, ELT, with its 39-meter mirror, is the most promising instrument for answering these questions. If ELT obtains a direct spectrum of Proxima b, this will be one of the most significant astronomical observations in history. If that spectrum contains O2, or the combination of O2 with CH4, molecules chemically incompatible without continuous biological replenishment, this would be an event comparable in significance to nothing else in the history of science. The detection of life in the nearest star system to us, at 4.24 light years. We do not expect this. Proxima b is more likely to show us something more prosaic, perhaps an atmosphere of CO2, perhaps signs of a waterless surface, perhaps nothing, which itself would be an answer. A negative answer is also an answer, and also changes our understanding of the galaxy. But the possibility, however small, exists. And it is not fantasy. It follows from physics and chemistry, from the laws to which everything in the universe is subject, including life. Life on Earth arose because conditions permitted. If conditions on Proxima b permit, or permitted, life could have arisen there too. Let us now talk about something that is both the most personally relevant and the most honestly stated thing about Proxima b, about what this planet means for us right now, tonight. Proxima Centauri is visible from the southern hemisphere, in the constellation Centaurus, about 2.2 degrees from the bright pair of Alpha Centauri A and B. From northern latitudes it stays below the horizon or barely rises above it. If you are in the southern hemisphere, find Centaurus. The brightest object in that region is Alpha Centauri A-B, the third brightest star system in the sky. Proxima is nearby, invisible to the naked eye at magnitude 11.1, but visible in binoculars under dark skies as a faint point near the brighter pair. When you look in that direction, you are looking toward the nearest star, toward the nearest potentially habitable world. Right now, as you stand outside, Proxima b is completing part of its 11-day year. The enormous dark red star stands motionless on its sky. Every few months, the star flares. The planet receives a pulse of radiation that would sterilize any unprotected surface. We do not know if there is an atmosphere protecting against this. We do not know if there is water. We do not know if there is life. But the planet is there, real or not, habitable or not, completing its rapid orbit right now, independent of whether we understand it or not. 4.24 light years. The nearest question the universe has posed. Let us talk about something that makes the Proxima b question more than just a single planet question. About what the answer would mean for our understanding of the galaxy as a whole. Red dwarfs constitute roughly 70 to 75% of all stars in the Milky Way. This is not a marginal population, it is the dominant stellar type. Most stars in our galaxy are small, dim, cool, magnetically active red dwarfs. Kepler statistics tell us that planets in the habitable zones of red dwarfs are common. Estimates range from about 20 to 50% of M dwarfs having planets in their habitable zones. Different studies give different numbers in this range. With 70% of stars being M dwarfs, most potentially habitable planets in the universe probably orbit red dwarfs. If the Milky Way contains roughly 100 to 400 billion stars, and 70 to 75% of them are red dwarfs, that is 70 to 300 billion red dwarfs. If 30% of them have planets in habitable zones, that is 20 to 90 billion potentially habitable planets around red dwarfs in our galaxy alone. This is an astronomical number. Even if only a tiny fraction of them are actually biologically habitable, the count of habitable worlds could be enormous. But if the conditions of Proxima b, superflares, atmospheric threat, tidal locking, cold trap, are typical for planets in the habitable zones of red dwarfs, and they probably are typical or close to it, then the question of whether these conditions support life becomes the question of whether most of the galaxy's potentially habitable real estate is actually inhabited. This is the deeper significance of Proxima b. It is not just one planet. It is the nearest representative of the most common type of potentially habitable planet. What we learn about Proxima b applies, with variations, to tens of billions of other worlds. If Proxima b is habitable, the galaxy is probably teeming with life. Life around red dwarfs everywhere. Life in conditions we considered hostile. Life that adapted to superflares and tidal locking the same way Earth life adapted to cold, to darkness, to acid, to radiation. If Proxima b is not habitable, if superflares and the absence of magnetic protection and the cold trap make red dwarf planets biologically barren, then most of the galaxy's habitable zones are empty. Life is rare. We are more alone than it seemed. Both possibilities are real. One of them is true. Proxima b knows which. Let us now talk about a specific example from our own solar system that illustrates that tidally locked worlds are not automatically lifeless, about Europa and Enceladus. Europa, Jupiter's moon, about 3,122 kilometers in diameter, is tidally locked. It always shows one face to Jupiter. It has no 24-hour day. It is covered in ice. Solar radiation on its surface is minimal. And yet, beneath Europa's icy crust lies a liquid ocean. Heated by tidal warming from gravitational interaction with Jupiter, the area of this ocean is roughly twice the area of Earth's world ocean. It is one of the most promising places to search for life in the solar system. Enceladus, Saturn's moon, is even smaller, diameter about 504 kilometers, and also tidally locked. Yet it has a subsurface liquid ocean that actively ejects water, organic molecules and hydrogen into space through geysers at its south pole. Both objects, tidally locked, far from the Sun, with surface ice and extreme surface conditions, have subsurface liquid environments potentially favorable for life. This precedent matters for understanding Proxima b. Even if the planet's surface is a radiation-sterilized desert, a subsurface environment could be different. If Proxima b has a rocky core with radioactive heating, as most planets do, and if above it lies a layer of ice, the nightside, or liquid water, subsurface habitability is not impossible. The difference between Europa and Proxima b is that Europa receives heat from Jupiter's tidal heating, a powerful source. Proxima b, if tidally locked in a nearly circular orbit, receives no significant tidal heating. The only internal heat source is radioactive decay in the core, which diminishes over time, and, for a planet 4.85 billion years old, is significantly weaker than in its youth. Nevertheless, for a planet of 1.27 or more Earth masses, radioactive heating sustains a molten interior long enough. Earth, 4.54 billion years old, still has active mantle convection and a liquid outer core. If Proxima b has an analogous or larger size, its interior is probably still hot. Let us now talk about the specific extremophile organisms on Earth that best illustrate what the potential range of life on Proxima b might look like. Deinococcus radiodurans, a bacterium that withstands radiation doses of 1.5 million rads. This is roughly 3,000 times the dose lethal to a human. It can repair its DNA damaged by hundreds of simultaneous double-strand breaks, using unique repair mechanisms. Named the most radiation-resistant organism by the Guinness Book of Records. Organisms at hydrothermal vents in ocean depths, in complete darkness, under enormous pressure, at temperatures up to 400 degrees Celsius, demonstrate that life does not require sunlight and is not limited to moderate temperatures. Psychrophiles, organisms adapted to extremely low temperatures. Bacteria have been found in Antarctic ice at -20 degrees Celsius. The nightside of Proxima b could have analogous conditions. UV-adapted organisms, such as certain cyanobacteria producing powerful protective pigments, can survive UV doses significantly above the Earth average. None of these organisms would survive Proxima b's open surface during a superflare, but they demonstrate how wide the range of physical conditions under which Earth life exists is, much wider than appears from the typical human experience. Real life on Proxima b, if it exists, would probably be microbial rather than multicellular. Multicellularity requires greater environmental stability than Proxima provides. Subsurface, living in rocks, in cracks, underwater, shielded from surface radiation. Chemotrophic, obtaining energy from chemical reactions, or using red and near-infrared light for photosynthesis, not sunlight in the Earth sense. Exceptionally radiation resistant, with DNA repair mechanisms significantly more powerful than any Earth organism. Let us now talk about the specific observational result that has provided the most precise independent confirmation of Proxima b's existence, about what Espresso found. Espresso, Eschel's spectrograph for rocky exoplanets and stable spectroscopic observations, is installed on the Very Large Telescope in Chile. It is the world's most precise spectrograph for radial velocity measurements, achieving precision of about 10 centimeters per second. For comparison, Earth causes the Sun to wobble at about 9 centimeters per second. In 2020, the Espresso team published an independent analysis of the Proxima Centauri system. Results confirmed the Proxima b signal with a period of about 11.2 days, though the authors noted some complicating factors related to stellar activity. More importantly, Espresso detected an additional signal with a period of about 5.15 days. This signal is interpreted ambiguously. It may be related to the stellar rotation period or its harmonics, or it may point to another planet, Proxima d, even closer to the star. In 2022, a paper was published claiming detection of Proxima d, a planet with mass about 0.26 Earth masses, on an orbit with period of about 5.15 days and distance of about 0.029 astronomical units from Proxima. If this is a real planet, it is one of the least massive ever detected by the radial velocity method. However, the status of Proxima d is even more uncertain than Proxima b. The signal is weak. Alternative explanations include stellar artifacts. The planet D has not been confirmed by independent methods. Nevertheless, if Proxima d is real, it is an even more extreme object than Proxima b. At 0.029 astronomical units, closer to the star than Proxima b, temperatures are higher, radiation more intense, tidal locking even more certain. This is definitively not a potentially habitable zone. But the presence of multiple planets in the Proxima system is important. It tells us the star went through a planet-forming process capable of producing several bodies. This makes the system richer and more interesting than if there were only one planet. Let us now talk about the most realistic concept for studying Proxima b in the foreseeable future, about the Breakthrough Starshot project and what it could actually achieve. Breakthrough Starshot, an initiative announced in 2016, funded partly by Yuri Milner with support from Stephen Hawking and others. Goal: develop and launch nanoprobes capable of reaching the Alpha Centauri system in 20 years. The concept: tiny probes the size of a postage stamp and weighing a few grams, equipped with a light sail. An array of powerful lasers on Earth accelerates the probes to 1/5 the speed of light. At 0.2 c, the distance to Proxima Centauri, 4.24 light years, is covered in about 21 years. Physically, this does not contradict known laws. Light does exert pressure on sails. With a sufficiently powerful laser source and sufficiently light sail, acceleration to percent fractions of the speed of light is theoretically possible. The practical difficulties are enormous. The laser array. To accelerate a probe to 0.2 c requires a laser array of about 100 gigawatts. This is several times the power of all power plants of some countries. The cost at current laser technology prices is hundreds of billions of dollars. The technology does not exist at the needed scale. The sail and probe. The sail must be nanometers thick and yet withstand the enormous impulse from the laser. The probe must contain a camera, spectrograph, power source, communication means, all in a few grams. This requires nanotechnology significantly more advanced than current. Navigation. At 0.2 c, the flyby through Proxima's system takes a few hours. During this time, all observations must be conducted, with no ability to stop or correct course. Any targeting error means the probe flies past. Communication. At 4.24 light years, the signal from the probe takes 4.24 years to reach Earth. Data collected during the flyby will arrive on Earth more than 20 years after launch and 4 years after the flyby. Dust grains. At 0.2 c, a collision with a dust grain a few microns in size is equivalent to a small explosion for the tiny probe. Interstellar space contains such grains. The probability of probe survival under these conditions is an open question. Despite all difficulties, Breakthrough Starshot is the most concrete and most funded initiative directed toward Proxima Centauri. Research work is underway. Progress in laser and nanotechnology is happening. Achieving this goal is possible, but more in a 50 to 100 year horizon than in the coming decades. Let us now talk about what living on Proxima b would actually require, about the specific practical problems if humans ever got there. The flight. At current technologies, about 73,000 years. At technologies that may be developed in coming centuries, possibly 20 to 30 years at laser-driven sail acceleration, or 100 to 200 years at nuclear pulse propulsion of a crewed ship. Neither option is realistic for the near future, but for the purposes of this conversation, let us assume humans got there. Radiation. A person on Proxima b's surface without protection during a superflare would receive a lethal ultraviolet dose in a few minutes, not hours, minutes. The constant radiation environment, even between flares, is significantly more aggressive than on Earth. Any human settlement would require either powerful underground shelter or exceptionally effective suit protection, or most likely both. Illumination. Dim reddish light on the day side, complete darkness on the night side. Permanent sunrise-like twilight at the terminator. None of these conditions is lethal in itself, but all of them are radically different from what the human organism is adapted to. Disruption of circadian rhythm from the absence of a 24-hour cycle would be permanent. Psychological factors. A motionless star in the sky. No sunrises and sunsets. No change of seasons if the orbit is circular and axial tilt is minimal. The same view on the day side, forever. Only weather changes, if weather exists, would break the visual monotony. Isolation. Any signal from Earth arrives with a 4.24-year delay. News from Earth is always old news. People you know, you see them as they were 4 years ago. If you sent a message home, the reply arrives in 8.5 years. Dialogue with family or friends becomes a rare exchange of letters that cross in transit. Generational isolation. The first generation of people on Proxima b will still remember Earth, personally. The second generation knows Earth only from parents' stories and messages arriving with an 8-year delay. The third, only from history. After several generations, Earth becomes a concept, not a place. This is a deep, existential situation for which we have no historical precedents. The first settlers in Australia were isolated from Europe by months, the early American colonists by weeks. But 4.24 light-years is categorically different. There it is impossible to return, only to continue living. Let us now talk about something that is both technically precise and philosophically significant, about what Proxima b's position in the galaxy actually tells us about the nature of habitability as a concept. We tend to think of habitability as a binary. Either a world is habitable or it is not. Earth is habitable. Mars is not, at the surface currently. Venus is not. But habitability is a spectrum, a gradient, and the relevant question is not just habitable or not, but habitable for what? Proxima b may be completely uninhabitable for the kind of life that exists on Earth's surface. The radiation environment, the tidal locking, the uncertain atmosphere, all of these work against complex surface life as we know it. But underground, in a subsurface ocean maintained by radioactive heating, the same planet might be entirely habitable for microbial life. The surface conditions are irrelevant to an organism living kilometers below. This is not a technicality. It reflects a genuine insight about life in the universe. The habitable zone concept was developed thinking about surface life requiring liquid water on the surface. Subsurface life does not need the star's warmth at all. It uses internal heat. The habitable zone for subsurface life extends to the outer solar system and potentially to rogue planets between the stars. Proxima b, sitting in the habitable zone of its star, is potentially doubly promising. It might support surface life if conditions are right, and it might support subsurface life through internal heating regardless of surface conditions. This duality is one of the reasons the planet is scientifically so important. It represents potentially two distinct habitability mechanisms operating simultaneously in a system we can actually probe from Earth. Let us now talk about the specific future timeline of what we expect to learn about Proxima b, and when, about the observational roadmap over the next 20 years. 2025 to 2028. The Vera Rubin Observatory's LSST begins systematic sky surveys. This will significantly expand the catalogue of known exoplanets and provide more precise positions for stellar systems. For Proxima Centauri, not directly about the planet, but improving the statistical context. Late 2020s. ELT, First Light and Early Science Operations. The 39-meter telescope begins observations. Initial attempts at direct imaging of Proxima b are among the highest priority science cases. Early results may be ambiguous, the technical challenge is extreme, but the first real opportunity to attempt direct detection. 2028 to 2035. ELT in full science operation. If the technical challenges are met, spectroscopic characterization of Proxima b becomes possible. The first spectrum of the planet's atmosphere, if it exists, could be obtained. This is when the fundamental questions, atmosphere, water vapor, oxygen, might begin to be answered. Gaia final data release. Gaia has been measuring stellar positions with extraordinary precision. The full data release includes multi-year time series that can detect the astrometric wobble of Proxima Centauri caused by its planet. This would provide independent mass conformation and orbital inclination, giving the true mass of Proxima b rather than just the minimum mass from radial velocity. 2030 to 2040. If early ELT results are promising, next-generation space-based direct imaging missions, concepts like the Habitable Worlds Observatory being studied by NASA, might be prioritized. These missions are specifically designed to image and characterize Earth-like planets around nearby stars. Beyond 2040. If any of the above returns evidence of an atmosphere, or better yet, biosignatures, the cascade of subsequent science would be enormous. Additional observations, more detailed characterization, debate, and verification. The decade after a biosignature detection at Proxima b would be the most scientifically intense in history. Let us now talk about one more specific aspect that reveals how connected the study of Proxima b is to the deepest questions in science, about the origin of life and whether the conditions at Proxima b could support abiogenesis. Abiogenesis, the emergence of life from non-living chemistry, is one of the most fundamental open problems in science. We do not know precisely how life originated on Earth. We do not have a well-preserved record of the first few 100 million years of life on Earth. What we know: life on Earth appeared relatively early, probably in the first 500 million years after the planet formed. This suggests that given the right conditions, the emergence of life can be a comparatively rapid process. But the right conditions are the key question. Does liquid water need to be present? Almost certainly yes. Is a source of chemical energy needed? Probably yes. Is sufficient chemical complexity needed? Probably yes. Is a specific temperature range needed? Unknown with precision. For Proxima b, if there is liquid water, if an atmosphere exists, if geological activity provides chemical energy, there are no fundamental prohibitions on abiogenesis. The conditions are harsh, but life on Earth did not arise in greenhouse conditions. Early Earth was also subject to intense bombardment, with unstable climate without an ozone layer. If life arises under conditions as difficult as early Earth, it will arise anywhere there is liquid water, chemical energy, and time. And Proxima b, if it has liquid water, has had about 4.85 billion years. If life arises only under very specific conditions rarely met, then even with liquid water on Proxima b, life may not have appeared. No answer exists. Let us now talk about the specific historical parallel that is most eloquent when considering our current position relative to Proxima b. In the Middle Ages and early modern period, European mariners knew of the existence of the Americas only through rumour and conjecture. The outlines of the continents were unknown, ocean depths unmeasured, currents unstudied, dangers undocumented, and yet ships departed. Not because they knew what awaited them, but because they did not know and wanted to find out. We are in an analogous position relative to Proxima b. We know it is there. We know some orbital parameters and mass. We know the star around which it orbits, but we do not know if there is an atmosphere, if there is water, if there is life. The difference? To America, the first ships sailed for a few months. To Proxima b, with current technologies, tens of thousands of years. With future technologies, possibly 20 to 50 years for a probe, centuries or more for a crewed mission. This means our voyage to Proxima b is a project not of one generation or one century. It is a civilizational project. A project requiring solutions to fundamental physical problems we have not yet solved. But this is not an unprecedented situation. The first people who left Africa 70,000 to 100,000 years ago did not know that after tens of generations their descendants would populate Australia, Asia, the Americas. They simply walked, generation after generation, moving into the unknown. If human civilization survives long enough, and if physics allows accelerating a ship to several % of the speed of light, then something like interstellar travel will eventually become real. And the first destination will be the nearest star, Proxima Centauri, and orbiting it, Proxima b. With all its difficulties, with all its uncertainty, with its superflares and possible cold trap and doubts about the existence of an atmosphere, all of this is the first page, not the last. Let us now talk about what remains the most important single fact about Proxima b, about what the combination of everything we have discussed tonight ultimately means. We know Proxima b probably exists. It is in its star's habitable zone. Its minimum mass is consistent with a rocky planet. We do not know whether it has an atmosphere, whether it has water, whether it has a magnetic field, whether it is tidally locked, whether it is geologically active. We suspect conditions there are significantly harsher than on Earth. Stellar flares create an extreme radiation environment. The atmosphere is threatened by stellar wind erosion. Tidal locking creates extreme thermal contrasts. The cold trap may have removed all surface water. Honest assessment: Proxima b is one of the most scientifically important objects in astrophysics and astrobiology, precisely because it is nearest and precisely because we know so little. But calling it a second Earth or our nearest habitable neighbour is wishful thinking. It may be habitable, it may harbour life right now, in subsurface or aquatic environments protected from surface radiation. Or it may be a bare, irradiated rock without atmosphere or water. We do not know. And that not knowing is one of the most exciting states in science. A question posed by the universe itself, at 4.24 light years, waiting for us to learn to read the answer. Let us talk about something that is rarely discussed in popular accounts of Proxima b, but that is fundamental to assessing whether life could persist there even if it arose. About the concept of biological continuity under periodic catastrophic events. Life on Earth has experienced mass extinctions. The end Cretaceous event 66 million years ago eliminated roughly 75% of species. The Permian Triassic event 252 million years ago eliminated perhaps 96% of marine species. These were catastrophic reductions in biological diversity from which recovery took millions of years. And yet, life continued. The key is that mass extinctions on Earth, however devastating, were not sterilizing events. Some fraction of species survived each extinction. From that surviving fraction, new diversity evolved. The question for Proxima b is whether superflares are analogous to mass extinctions, devastating but survivable events from which life can recover, or whether they are sterilizing events that eliminate life entirely each time they occur. This depends critically on the dose received and the degree of protection available. On the open surface of Proxima b, without atmosphere or magnetic field, a major superflare would likely be a sterilizing event for surface life. The UV doses at the levels estimated for the 2019 event would destroy organic molecules at the surface, not just kill organisms. But sterilization of the surface is not sterilization of the planet. Underground organisms, aquatic organisms, organisms under rock or ice, these are shielded. The surface sterilization would not reach them. If life exists in subsurface environments on Proxima b, superflares are irrelevant to its survival. It never encounters the surface radiation, regardless of how intense the flare. It lives in the same thermal and chemical environment, whether the star is quiescent or exploding. The scenario this suggests, any life on Proxima b is almost certainly subsurface. Not surface life that has adapted to survive flares, but life that never engages with the surface at all. Life that chose, evolutionarily speaking, to remain underground or underwater, and for which the surface is as hostile as vacuum is to us. This is actually not unusual by Earth standards. The subsurface biosphere on Earth, organisms living in rock pores, hydrothermal systems, deep aquifers, is thought to contain as much biomass as the surface biosphere. Life underground on Earth is the rule, not the exception. Proxima b may be a world where the underground biosphere is the only biosphere, not because surface conditions prevented the evolution of surface life, but because the underground environment is simply where life stayed once it originated. Let us now talk about a specific physical comparison that makes the scale of the superflare problem viscerally concrete, about what the 2019 Proxima superflare would have done to Earth if it had happened to the Sun. The 2019 Proxima superflare increased the star's luminosity roughly 14,000 times at peak. For a few minutes, Proxima was 14,000 times brighter than normal. Our Sun, at normal luminosity, delivers about 1,361 watts per square metre at Earth's distance. If the Sun suddenly became 14,000 times brighter for a few minutes, Earth's surface would receive about 19 million watts per square metre of combined radiation. This is not survivable in any conventional sense. The entire atmosphere would be subject to extreme photochemical disruption. The ozone layer would be massively depleted, possibly stripped away entirely in the affected hemisphere in minutes. Even with Earth's magnetic field protecting against charged particles, the photon radiation, UV and X-ray, would not be deflected. Recovery from a solar equivalent of the 2019 Proxima superflare would take years to decades as the ozone layer slowly rebuilt. During that period, surface UV levels would be dramatically elevated, potentially mass extinction level for surface life. And this happened at Proxima several times in the months surrounding the 2019 observation. It is not a once-per-millennium event. It is essentially routine. This is what makes Proxima different from an Earth-like environment in a way that goes beyond merely difficult. The periodic sterilizing events are so routine that they are built into the background conditions. Any life that exists there has evolved not despite them, but within a framework where they are a regular feature of the environment, like winter is to temperate zone organisms on Earth. Let us now talk about what the first direct detection of Proxima b's atmosphere would actually look like, about how the science would unfold if ELT succeeds in obtaining a spectrum. Imagine it is 2031. The extremely large telescope has been operating for 3 years, and the team attempting direct imaging of Proxima b has finally achieved the required contrast ratio after years of instrument refinement. The first data comes in. What they would see, or try to see, is a point of light separated from Proxima Centauri's overwhelming glare by the coronagraph. The planet would be perhaps 40th magnitude at best, about 10 billion times fainter than the star. Separating this point from the residual starlight after coronagraphic suppression is the fundamental technical challenge. If they succeed, the first thing determined is whether the spectrum of the point source is consistent with a planet. Does it reflect the star's red spectrum appropriately? Is the brightness consistent with a rocky planet at this distance? If yes, the next question is the atmospheric spectrum. Different atmospheric compositions leave different imprints on the reflected starlight. Carbon dioxide has absorption features around 1.6 and 2.0 microns in the near-infrared. Water vapor has features at 1.4 and 1.9 microns. Oxygen has a feature at 0.76 microns, methane at 2.3 microns. A single spectrum with enough signal-to-noise to detect these features would require combining many hours or nights of observation. But ELT, with its 39-meter light-collecting area, makes this achievable in principle. The announcement would be extraordinary even in the case of a relatively boring result. CO2 and N2 with no oxygen, a Venus analogue or Mars analogue atmosphere. Still extraordinary, the first direct atmospheric characterization of the nearest exoplanet. A confirmation that Proxima b has an atmosphere at all, a profound first step.
The extraordinary case, if oxygen is detected alongside water vapor, would trigger immediate intensive follow-up, not just from ELT, but from every large telescope on Earth and in space that could contribute. The combination of water and oxygen in a planetary atmosphere is strongly suggestive of biological activity, not proof, but a signal demanding explanation. The science team would spend years ruling out abiotic explanations before being willing to claim a biosignature. This is how the discovery would actually unfold, not as a single announcement, but as years of patient verification, each step narrowing the possibilities, each paper adding to the case, until either the biological interpretation becomes untenable or it becomes the most parsimonious explanation. We are perhaps a decade from this moment being possible, perhaps more. Perhaps the technical challenges are greater than current estimates. Perhaps the planet turns out to have no detectable atmosphere at all. But the scenario is real. The physics permits it. The instruments being built can, in principle, achieve it. Let us now talk about something that connects the science of Proxima b to the broadest philosophical framework, about what finding or not finding life at 4.24 light-years would mean for the Fermi paradox. The Fermi paradox asks, if intelligent life is common in the universe, where is everybody? Given the age of the galaxy, roughly 13 billion years, any civilization that developed interstellar travel even a few million years ago should have had time to spread throughout the galaxy. We see no evidence of this. Where are they? The discovery of life at Proxima b, even microbial, even simple, would transform the Fermi paradox fundamentally. If life exists at the nearest star, at 4.24 light-years in a galaxy 100,000 light-years across, then life must be, essentially, everywhere. It must be so common, arising so readily wherever conditions permit, that the galaxy is saturated with it. This makes the silence even more puzzling. If life is everywhere, why has none of it developed intelligence, technology, and interstellar presence detectable from Earth? One resolution: life is common, but intelligence is rare. Single-celled life might arise readily wherever conditions allow, but the specific evolutionary steps leading to complex multicellular life, then to intelligence, then to technology, might be so improbable that in 13 billion years very few civilizations have arisen. The galaxy is full of microbes mostly, and the silence is because microbes do not build radio telescopes. Another resolution: life is common, intelligence arises, but civilizations typically destroy themselves or choose not to expand. The silence reflects not rarity, but some universal tendency towards self-limitation. Another: the galaxy has been colonized, but not by us, and not in ways we recognize. The assumption that interstellar colonization would be obvious is perhaps wrong. None of these resolutions is obviously correct. The discovery of life at Proxima b would not directly answer the Fermi question,
but it would transform the landscape of possible answers by eliminating the simplest resolution, that life itself is extremely rare and we are essentially alone. Conversely, if the nearest potentially habitable planet is confirmed lifeless, if our most thorough examination of the nearest habitable zone planet shows a barren rock, this would push toward the conclusion that life is rarer than we hoped. That the conditions producing life on Earth were more special than they appear. This too would be an important answer, perhaps the most important negative result in the history of science. Let us now talk about something that exists at the intersection of the practical and the profound, about what it will feel like to be the person who obtains the first spectrum of Proxima b's atmosphere. Science is often described in terms of results, papers, data, discoveries, but science is also a human experience. Someone will be the person who first looks at the spectrum of Proxima b and sees the absorption features of its atmosphere, or who looks at the spectrum and sees nothing, a bare rocky surface, no atmosphere. That moment, whenever it comes, will be singular, more singular than any moment in the history of planetary science, because every other planetary observation, however extraordinary, was of a world in our own solar system, or a statistically anonymous world among thousands of known exoplanets. Proxima b is neither of these things. It is the nearest world, the first star out, the destination of every future interstellar mission, the representative of 70% of the galaxy's stars. The nearest answer to the question of whether we are alone. The person who first reads that spectrum will know something, definitively, observationally, empirically, about the nature of life in the universe that no human has ever known. Whether the spectrum shows an atmosphere rich in signs of chemistry compatible with life, or whether it shows a dead, airless rock, they will know which. This will be one of the defining moments in the history of human knowledge, not because of what is at Proxima b specifically, but because of what it tells us about everything else, about the 70% of stars, about the tens of billions of habitable zone planets, about whether the galaxy is full or empty. The spectrum is out there. The photons from Proxima b are hitting the Earth right now, reflecting off the planet's surface, passing through its atmosphere, if it has one, crossing 4.24 light years, arriving at our instruments. We just need better mirrors to read them. Let us now talk about a specific aspect of the Proxima b question that is underappreciated, about the role of geological time in any assessment of the planet's current state. Proxima Centauri is estimated to be about 4.85 billion years old, slightly older than our Sun, 4.6 billion years, and our solar system, 4.57 billion years. This is an important context. The harshest phase of stellar activity for a red dwarf is its pre-main sequence phase, the period before nuclear burning stabilizes the star, when it is much brighter and more active than later. For Proxima-sized stars, this phase can last from a few 100 million years to over 1 billion years. If Proxima's planet-forming period coincided with this early high-activity phase, the young Proxima b would have faced conditions even more extreme than today. More luminosity, more heating, potentially triggering the runaway greenhouse, more UV and X-ray flux, stronger stellar wind. Anything that happened to Proxima b's water and atmosphere in those first few 100 million years was happening to a planet that also had much greater internal heat from its own formation, more radioactive elements active, more geological activity, more outgassing. The competition between atmospheric erosion from the star and atmospheric replenishment from volcanic outgassing in those early billions of years determines what we would find today. A planet that lost the battle, dominated by erosion,
is a dry, airless rock today. A planet that won, or drew the battle, that maintained enough geological activity to keep the atmosphere replenished, might have a stable atmosphere today, even after 4.85 billion years. We do not know which Proxima b is. We cannot know without observing it.
But the geological time aspect adds another layer to the uncertainty. The current state of the planet is the outcome of 4.85 billion years of competition between destruction and replenishment, and we are only now developing the tools to see which side won. Let us now talk about what distinguishes our current era from all previous eras in terms of our ability to actually answer the question of Proxima b's nature. For all of human history before 1992, we had no confirmed planets beyond our solar system. For all of human history before 2016, we had no confirmed planet around the nearest star. For all of human history before the 2020s, we had no instrument capable of directly characterizing the atmosphere of a nearby Earth-size planet. We are right now in the transition period, the era when the tools are being built, ELT under construction, JWST operating, next-generation space missions being designed, and the era when the answers become possible begins within a decade. The generation of astronomers currently in graduate school will be the generation that obtains the first spectrum of Proxima b, the generation that determines whether there is an atmosphere, the generation that either finds the first biosignatures or rules them out at the nearest star. This is an extraordinary historical moment, comparable in some ways to the decade before the discovery of the telescope, when the question was already being asked and the instruments capable of beginning to answer it were being developed. Or comparable to the 1980s in molecular biology, when the tools for reading DNA were being developed and the answers to fundamental questions about the mechanism of life were about to become accessible. We are not at the answer yet, we are at the threshold. The tools are being built, the planet is there. And the answer, whatever it is, will change how we understand our place in the universe permanently. The question is simply which answer it will be. Let us talk about something that is both technically specific and philosophically expansive, about what the study of Proxima b has already taught us, even before we have definitively characterized the planet itself. The discovery of Proxima b in 2016, or the near-certain candidate acknowledging the ongoing debate, triggered an explosion of theoretical work. Hundreds of papers modelling the atmospheric dynamics, the stellar-wind interaction, the tidal locking consequences, the radiation environment, the potential for subsurface oceans, the chemistry of possible tholins on the surface. This theoretical work has value independent of whether Proxima b turns out to be habitable. It has sharpened our understanding of what happens to planets near red dwarfs in general. It has produced physical models that apply to the tens of billions of red dwarf planets in the habitable zones of our galaxy. It has refined the questions we need to ask and the measurements we need to make. Before 2016, the habitability of red dwarf planets was a relatively underdeveloped topic. A few theoretical papers existed, but the field was not considered urgent because no specific nearby target existed. After 2016, with a specific world at 4.24 light-years suddenly demanding understanding, the field exploded. The number of papers on M-dwarf planet habitability roughly tripled within 5 years of the Proxima b announcement. This is how science works. A specific question, is this specific planet habitable, drives generic understanding of the entire class. The answer for Proxima b specifically matters,
but the theoretical framework built in pursuit of that answer matters for all red dwarf planets. Similarly, the observational programs designed to characterize Proxima b will produce instruments and techniques applicable to every other nearby, potentially habitable planet. The coronagraph designs for ELT being developed partly to image Proxima b will be the same coronagraphs used to study other nearby worlds. The atmospheric retrieval algorithms being refined to interpret red dwarf planet spectra will be the algorithms used across the field. Proxima b is simultaneously a specific question and a driver of general capability. Even if the planet turns out to be unambiguously barren, a dry, airless rock with nothing of biological interest, the effort to characterize it will have produced tools and knowledge valuable for the entire field. Let us now talk about the specific way that stellar flares at Proxima interact with a possible planetary atmosphere, about the chemistry of what happens to nitrogen and oxygen under intense UV bombardment. On Earth, the stratospheric ozone layer is maintained by a photochemical cycle. Oxygen molecules, O2, are split by UV to produce atomic oxygen, which combines with O2 to form O3, ozone. The ozone then absorbs UV and is itself split, releasing atomic oxygen to start the cycle again. During strong UV events, like solar flares, this cycle is disrupted. Intense UV and X-ray radiation produces nitrogen oxides in the upper atmosphere through energetic reactions. Nitrogen oxides catalytically destroy ozone, the same mechanism responsible for the Antarctic ozone hole, where chlorofluorocarbon compounds rather than nitrogen oxides are the primary culprit. But the catalytic ozone destruction is chemically analogous. After a major solar flare on Earth, ozone depletion in the polar regions has been measured. The effect is real and temporary. The ozone recovers over months as the nitrogen oxide concentration returns to normal levels. For Proxima b, the same chemistry applies, but with very different parameters. Superflares at Proxima are thousands of times more energetic than the most powerful solar flares. The nitrogen oxide production during a superflare would be enormous. Ozone depletion during and after a major superflare could be nearly total. The ozone layer stripped to essentially nothing for months, while the nitrogen oxide chemistry slowly relaxes. During this recovery period, before the ozone layer rebuilds, the surface is exposed to unshielded UV, which means that even with an Earth-like ozone layer under normal conditions, the ozone is periodically stripped by superflares and then must rebuild. The surface cycling between ozone-protected and ozone-depleted periods several times per year. This creates a more complex picture than simply no ozone layer versus full ozone layer. The question becomes, how quickly can the ozone layer rebuild after a superflare? How long is the surface exposed to dangerous UV between flare-driven depletion and ozone recovery? Research suggests the recovery timescale could be weeks to months, depending on the severity of the flare and the total atmospheric composition. During those weeks to months, surface life without other UV protection would face essentially unshielded radiation. Life on Earth that evolved under such a cycle, periodic ozone depletion followed by recovery, would likely have developed robust UV protection that is operational at all times, rather than relying on the ozone shield. Dark pigments, thick protective outer layers, rapid DNA repair that activates during high UV periods, behavior that drives organisms underground during acute flare events. This is not impossible to imagine evolutionarily, but it requires that the initial origin of life occurred and early life survived long enough to develop these protections. The early stages,
before DNA repair mechanisms and UV protective pigments evolved, would have been the most vulnerable period.
If the UV doses during early Proxima b history were as intense or more intense than today, this early vulnerable period might have been severe enough to repeatedly suppress the emergence of surface life. Let us now talk about a specific comparison that illuminates how we should think about the probability of life on Proxima b, about the difference between the probability that life exists there and the probability that we could detect it if it does. These are two entirely different questions that often get conflated. The probability that life exists on Proxima b is genuinely unknown. It could be anything from essentially zero to relatively high. We do not have enough data to constrain it meaningfully.
Arguments pointing toward possible habitability, liquid water possible, long time available, red dwarfs common, meaning life at red dwarfs would be advantageous by sheer numbers, and arguments pointing against, superflares, atmospheric threat, tidal locking, are roughly balanced given current knowledge. But the probability that we could detect life on Proxima b, if it exists, that is a different and in some ways more tractable question. If life exists only in the deep subsurface of Proxima b, in rocks or in subsurface oceans, with no biological modification of the atmosphere, then we almost certainly could not detect it from Earth, even with ELT. Subsurface life that produces no atmospheric biosignatures is essentially invisible to remote sensing. We could visit the planet, drill and sample, but from here, remotely, nothing. If life exists and has modified the atmosphere, produced oxygen through photosynthesis or methane through metabolism or other detectable compounds, then ELT in principle can detect these signatures. This would require life that is at least somewhat photosynthetically active near the surface, producing gas phase byproducts that enter the atmosphere. On Earth, the biosphere produces oxygen through photosynthesis, methane through microbial and animal metabolism, nitrous oxide through microbial metabolism, dimethyl sulfide from marine phytoplankton, and other compounds, all of which create an atmospheric composition profoundly different from what chemistry alone would produce. Earth's atmosphere is a massive biosignature visible from space. Proxima b's atmosphere could be equally modified if life has been active there for billions of years.
But only if the life is metabolically and photosynthetically active enough to produce atmospheric compounds in significant quantities, and only if those compounds are not immediately destroyed by the intense UV bombardment. Here is the uncomfortable possibility. Life might exist on Proxima b, but in a form that produces no detectable atmospheric biosignatures. Purely chemotrophic subsurface life that never engages with the atmosphere. In this case, the planet is inhabited, and ELT would tell us it is barren. A false negative. We would conclude no life and be wrong. This possibility exists and cannot be dismissed. The detection of life via atmospheric biosignatures is a biased probe. It detects the specific kind of life that modifies atmospheres. Other kinds of life, potentially just as complex and diverse, are invisible to this method. Acknowledging this does not make atmospheric biosignature searches less valuable. They are the only practical remote method we have.
But it means that a negative result, no biosignatures detected, is not proof of no life. It is proof of no detectable life, which is a different and weaker conclusion. Let us now talk about the specific way the Proxima b question illustrates a broader principle in science, about the distinction between what we can observe and what is actually the case. All of observational science operates under this constraint. We do not observe reality directly. We observe whatever our instruments can detect, and we infer reality from what our instruments detect. For most of science, most of the time, this is not a troubling problem. Our instruments are sensitive enough to capture what matters, and the gap between what we observe and what is real is small. For Proxima b, the gap is enormous. We are inferring the existence of a planet from a small periodic wobble in the radial velocity of its star. We are inferring its mass from the amplitude of that wobble. We know almost nothing about its surface, atmosphere, or interior. Even if we obtain a spectrum with ELT, we will be observing light reflected from or transmitted through the top layers of the atmosphere. We will infer surface conditions from atmospheric signals. We will infer the presence or absence of biology from chemistry. Each inference step introduces uncertainty. The gap between data and reality grows with each step. This is not a problem unique to Proxima b, but Proxima b makes it unusually visible because we care so much about the answer, and the answer is so hard to get. We want to know if there is life. We can measure reflected photons from the top of an atmosphere 4.24 light-years away. The distance between what we want to know and what we can measure is vast. Bridging that distance requires inference, and inference requires assumptions, and assumptions can be wrong. This is why scientific humility about Proxima b is not pessimism, it is epistemic precision. Saying we do not know whether Proxima b is habitable is not saying we cannot find out. It is accurately describing where we are in the process of finding out. And the process is real. The planet is real. The photons are real. The mirrors being built are real. We are in the middle of finding out. Let us now talk about what the specific night sky observation tonight can tell you about the broader context of everything we have discussed, about what to think about when you look toward the constellation Centaurus. Whether or not Centaurus is visible from your latitude tonight, you know it is there. In the direction of the southern sky, behind the horizon if you are in the northern hemisphere, there is a star system containing a planet that may or may not be habitable, that we have been able to see only as a tiny periodic wobble in a spectrum, that we have never directly imaged, that we know only through inference and mathematics and the accumulated theoretical work of hundreds of scientists across a decade. That planet, 4.24 light-years away, is currently completing another orbit. It has been completing orbits for 4.85 billion years. It will continue completing orbits whether we ever figure out what it is like or not. What has changed in the last decade is that we now know it is there, or very probably there, and we know with increasing precision what the question is, what specific measurements would tell us whether it is habitable, whether it has an atmosphere, whether it has water, whether it might harbour life. The question has sharpened.
The tools to answer it are being built. The people who will answer it are working today. This is an extraordinary moment to be alive. After we discovered the question, and before we have the answer. After we found the planet, and before we know what it is. In the window, when everything is still possible, habitable or barren, with life or without, with an atmosphere or naked rock. And when the actual observations that will resolve this remain just slightly beyond our current reach. That window will close, probably within the next 15 to 20 years, with ELT, with improved space-based instruments, with cumulative data from multiple observatories. The question of Proxima b's atmosphere will be answered. Life or no life will narrow from question to data. We live in the last years of the window when the question is still completely open. That is a remarkable place to be. Look toward the south tonight, or simply know it is there, in the direction of the sky that curves away from you toward the southern hemisphere. Proxima Centauri, 4.24 light-years, the nearest star, and around it a planet completing its 11-day year right now.
a planet we have never seen, a planet we are only beginning to understand. The nearest question posed by the universe, waiting for us to develop the instruments to read it. Let us talk about something that connects the Proxima b question to the deepest uncertainty in all of astrobiology, about whether the origin of life is a common or rare event, and why the answer determines everything. We have one data point for the origin of life: Earth. On Earth, life arose relatively quickly, within the first billion years, possibly within the first few 100 million years after conditions became suitable. This single data point is simultaneously our most important piece of evidence and the most dangerous, because one data point tells us almost nothing about frequency. Imagine you flip a coin once and it comes up heads. What is the probability of heads? You cannot conclude from one flip. The coin might be fair, 50% heads, or it might be double-headed, 100%, or it might be heavily weighted, 70%. One outcome cannot distinguish between these possibilities. The origin of life on Earth is like one flip of the cosmic coin. Life arose here. Does that mean life arises readily wherever conditions are suitable? The coin is double-headed. Life always wins. Or does it mean we were astronomically lucky? The coin comes up heads once in a billion flips, or something in between. We genuinely do not know. The philosophical and scientific debate on this question, known as the rare Earth hypothesis versus the mediocrity principle, has been running for decades without resolution. The rare Earth hypothesis argues that the specific conditions producing complex life on Earth are so improbable that Earth-like worlds with life are extremely rare in the galaxy. The mediocrity principle argues that Earth is not special and that life arises wherever conditions allow, making life common. Both hypotheses are consistent with current evidence because our evidence is so limited. We have one example of life and no examples of its absence at comparable scales. We cannot distinguish between a universe full of life and a universe with only us from our current observational position. This is where Proxima b becomes potentially decisive. If we find life at 4.24 light-years at the nearest star, we have now flipped the coin twice and gotten heads twice. This strongly suggests the coin is weighted toward heads. Life at the nearest star would be almost definitive evidence that life is common, because the nearest star is essentially our cosmic neighborhood. And if life exists in our neighborhood, it almost certainly exists throughout the galaxy. If we examine Proxima b thoroughly with the best instruments available and find a dead, barren world with no biosignatures, no indication of current or past life, then we have one data point of life, Earth, and one data point of no life, Proxima b. Still insufficient to conclude definitively, but the absence of life at the nearest potentially habitable planet would shift the probability distribution. It would make the rare Earth hypothesis somewhat more credible. If we examine multiple nearby potentially habitable planets over the coming decades, Proxima b, planets around nearby M-dwarfs like TRAPPIST-1, 39 light-years away, LHS 1140, 48 light-years away, GJ 667c, 22 light-years away, and find none of them show biosignatures, the evidence for rare Earth accumulates. Conversely, if even one of them shows unmistakable signs of life, the mediocrity principle gains strong support. Proxima b is the first of these examinations, the nearest, the most practical in the near term. What we find there is the first piece of evidence for the most important question in science. Let us now talk about what the specific physical environment of the terminator zone would actually be like, about the details of what the most habitable region of Proxima b would look like if you were standing in it. The terminator zone of Proxima b is the narrow band running from pole to pole along the boundary between the perpetually lit day side and the perpetually dark night side. Here, Proxima Centauri hangs perpetually just at or near the horizon, never rising, never setting, just hovering. What would this look like? The star itself. At 0.0485 astronomical units from Proxima, with the star having an angular diameter roughly 3 times larger than the Sun appears from Earth, the star occupies a large portion of the horizon. Not a disk you can look at directly, far too bright, even dimmed relative to the Sun, but a large glowing object filling the horizon. Imagine a sunset where the sun never actually sets. The horizon permanently orange-red with the star hovering just above it. The sky colour. With an Earth-like atmosphere, Rayleigh scattering by atmospheric gases produces the blue colour of Earth's sky. But Proxima's spectrum peaks in the red and near infrared. With less blue light available to scatter, the sky in the terminator zone would be less brilliantly blue than Earth's and more amber or reddish-orange, especially near the horizon where the star sits. The shadows. Because the star is always near the horizon, all shadows are long. Nothing ever produces a short shadow at high sun angle because the star never gets high. Every object on the surface of the terminator zone would be in perpetual late afternoon long shadows, pointing away from the star. The temperature. In the terminator zone, with a suitable atmosphere, perhaps similar to a temperate spring or autumn day on Earth, the star's heating is less intense than the day side, but not negligible. Atmospheric circulation bringing heat from the day side warms the terminator. Wind, probably persistent, blowing from the warmer day side toward the cooler night side, creating a prevailing wind system unlike any on Earth, where wind is driven by the day-night cycle. The night sky. Look away from the star toward the night side, and the sky is filled with stars. Not from above, but from the hemisphere of sky not occupied by Proxima. With no star ever overhead in the day side direction, the terminator sky has a unique geometry. Stars are visible continuously in the night side hemisphere. Among them, 2 very bright objects, Alpha Centauri A and B. From Proxima's distance of 0.21 light-years from the Alpha Centauri binary, those 2 stars would appear as magnitude -6 objects, strikingly bright, casting faint shadows at night. The weather. Atmospheric circulation modelling suggests that the terminator zone would have persistent patterns driven by the permanent temperature gradient from day side to night side. Clouds might form preferentially at the terminator as warm, moist air from the day side meets cooler conditions. There might be persistent terminator weather systems, cloud bands, circulation patterns, perhaps rainfall. Unlike Earth, where weather patterns drift eastward or westward with the planet's rotation, on Proxima b, the patterns would be locked to the geography of dayside and nightside. The geology. If Proxima b is volcanically active, volcanic eruptions would create the same kinds of landforms as on Earth, but in a context where no rain wears them down on the night side, too cold, and intense heating modifies them on the day side. The terminator zone might be geologically the most interesting region, where liquid water, if any survives, meets rock, where atmospheric interactions with the surface are most complex. Standing at the terminator of Proxima b, the overall impression would be unmistakably alien. The enormous dim red star perpetually at the horizon, the amber-coloured sky, the permanent long shadows, the persistent wind from the day side, the brilliant double point of Alpha Centauri in the night side sky. and the silence of a world with no birds, no insects, no rustling leaves, or the sound of whatever has evolved there, if life exists. It would be unlike any place on Earth. But it would not be obviously hostile in the way the surface of Mars is obviously hostile, where the thin atmosphere, the lack of liquid water, and the radiation environment are immediately apparent threats. Proxima B's terminator zone, with a suitable atmosphere, might feel merely profoundly alien rather than immediately lethal. Merely alien. Let us now talk about what the study of Proxima b reveals about the relationship between science and patience, about how the most important questions sometimes require decades or generations to answer. We discovered Proxima b in 2016. We will not have a definitive atmospheric characterization until the 2030s at earliest. That is a minimum of 15 to 20 years from discovery to first serious characterization. And characterization will not itself be the final answer. After the first spectrum comes years of interpretation, alternative explanations to rule out, additional observations to build the case. The detection of biosignatures, if they exist, would likely not be a single moment of clarity, but a gradually strengthening case built over years of observations. No single spectrum will say, this planet has life. What accumulates is evidence, each piece adding to the weight of the case, each alternative explanation ruled out by the next observation, until the only remaining explanation is biological. This is a deliberate and potentially decade-long process. It requires patience. But this patience is not unique to Proxima b. The history of science is full of questions that required patience measured in generations. The nature of light, wave or particle, debated for centuries before quantum mechanics resolved it. The structure of the solar system, centuries of gradual refinement from geocentric to heliocentric to dynamical models. The age of the universe, contested through much of the 20th century before converging on the current figure. The biggest questions take the longest to answer. The smallness of the answer space, that it must be one specific thing, and the difficulty of the evidence required to distinguish between possibilities, means that the most important questions resist quick resolution. Life on Proxima b is one of the biggest questions. It will not be answered quickly. The people working on it today may not live to see the final answer. The graduate students entering this field now will spend their careers building toward an answer that their students might finally confirm. This is not discouraging. This is the scale of the question. Questions of this magnitude deserve patience. They deserve careers and generations of effort. And right now, at this specific moment in history, we are in the early phase of that effort. We have the question. We are building the tools. The answer is coming, slowly, through hard work and patience and accumulated evidence, but it is coming. Let us now talk about a specific analogy that helps situate Proxima b in the history of human exploration, about what it means for a world to go from unknown to known. In 1519, Ferdinand Magellan departed Spain with 5 ships. His goal was to circumnavigate the globe, something no expedition had achieved. He did not know exactly what he would find. The Pacific Ocean was largely uncharted by Europeans. The scale of the world beyond Europe was unclear. What Magellan's expedition proved, at enormous cost, with the loss of most of the crew, including Magellan himself, was that the world is continuous and connected, that the oceans join, that a ship sailing west eventually reaches the east, that the world is a specific, finite,
navigable thing rather than an unlimited expanse of unknown. Before the expedition, the world was largely unknown. After, it was known in its broad outlines, even if details remained to be filled in for centuries. Proxima b represents a similar threshold. Before 2016, we did not know there was a planet at the nearest star. Now, we almost certainly know there is. Before ELT's observations, we will not know if it has an atmosphere. After, we will know, at least in broad outline. Each step reduces the unknown. Each measurement fills in another portion of the map. The world goes from mystery to knowledge. Not all at once, not completely, but progressively and irreversibly. Magellan's expedition also demonstrated the true scale of the Pacific. Sailors had underestimated how large the ocean was. The crossing was much harder and longer than anticipated. The cost was much higher. The same may be true of the Proxima b exploration. The technical difficulties may be greater than current estimates. The timeline may be longer. The cost, in telescope time, in scientific effort, in resources, may exceed projections. But the direction is clear. The question is specified. The tools are being built. The knowledge will come. Just as the Pacific crossing eventually became routine once the routes were established, the characterization of nearby exoplanet atmospheres will eventually become routine once ELT and its successors demonstrate it is possible. The first crossing is always the hardest. Proxima b is the first crossing, the nearest star, the first atmosphere to characterize, the first search for biosignatures in another stellar system. Everything that comes after, the survey of the nearest 100 stars, the systematic inventory of nearby habitable worlds, the eventual detection or definitive absence of life in our stellar neighborhood, comes after this first crossing. We are preparing for the crossing now. Let us now talk about what is most worth holding on to from everything we have discussed tonight, about the single most important truth about Proxima b that survives all the complexity and uncertainty. The most important truth is not the superflares, not the tidal locking, not the cold trap or the uncertain atmosphere or the debated confirmation status. The most important truth is this. We live in the first period of human history when the question of life beyond Earth is becoming an empirical question rather than a philosophical one. For all of human history before now, the question of whether life exists beyond Earth was philosophical. You could argue for or against it. You could construct elaborate frameworks, but you could not test it. You had no observations, no data, no measurements that could in principle distinguish between a universe full of life and a universe with only us. Now, for the first time, we have specific planets, specific stars, specific targets at which we can point specific instruments and obtain specific spectra that will contain or not contain specific biosignature molecules. The question has moved from the realm of philosophy into the realm of science. It is now a question that can, in principle, be answered empirically. Proxima b is the nearest and most immediate example of this transition. It is the planet that most clearly represents the shift from "we cannot know" to "we are learning to look." This transition, from philosophical speculation to empirical investigation, is one of the great transitions in intellectual history. Comparable to the transition from alchemy to chemistry, from astrology to astronomy, from natural philosophy to physics, from theology to biology. Each of these transitions moved a domain from the realm of belief and argument into the realm of evidence and experiment. The question of life in the universe is making this transition now, in our lifetime,
in the next 15 to 30 years. Proxima b is the first chapter, the nearest star, the nearest question, at 4.24 light-years. Go outside tonight, find the south, or simply face the direction where the sky curves toward the southern hemisphere. Proxima Centauri is there, behind the horizon if you're in the north, visible low in Centaurus if you're south of roughly 30 degrees north latitude. You cannot see Proxima with the naked eye. It is magnitude 11, far below the limit of human vision without a telescope. But knowing it is there changes what it means to look in that direction. 4.24 light-years, the nearest star. The light reaching your eyes right now from that region of the sky left Proxima Centauri 4 years and 3 months ago. The star you are looking toward in the direction of Centaurus has been burning for 4.85 billion years, slightly longer than our Sun. It will burn for hundreds of billions more.
Long after the Sun has exhausted its fuel and expanded into a red giant and collapsed into a white dwarf, Proxima Centauri will still be burning. Dim, red, steady, lasting. And around it, almost certainly, a planet, Proxima b. Right now, as you stand outside, it is completing another portion of its 11-day year. An enormous dark red star stands motionless on its sky, never rising, never setting, simply there. The star that is its entire source of warmth and light and radiation. The star that several times a year erupts in superflares, thousands of times more powerful than the greatest solar storms ever recorded. We do not know if there is an atmosphere protecting the surface from those flares. We do not know if there is water. We do not know if the planet is tidally locked, though physics strongly suggests it is. We do not know if a magnetic field exists to shield whatever atmosphere might be there from the relentless stellar wind. We know almost nothing about what it is actually like, and this is extraordinary. The nearest potentially habitable planet to Earth, the first destination of every future interstellar mission, the representative of 70% of the galaxy's stars, the world that holds within it the answer to whether the galaxy is full or empty of life, and we know almost nothing about it. We have detected it as a wobble, a tiny, periodic variation in the speed of a star moving toward us and away from us, a signal in the spectrum of a magnitude 11 red dwarf. This is all we have. This and the theoretical work of hundreds of scientists modelling what it might be like based on physical laws and analogies to things we do understand. It might have an atmosphere of nitrogen and carbon dioxide. It might be a bare rock baked by flares and stripped by stellar wind. It might have liquid water in a narrow terminator band where a perpetual twilight reigns and the enormous red star perpetually hovers just above the horizon. It might have a subsurface ocean warmed by radioactive decay, filled with chemistry, possibly hosting microbial life that has never seen the surface or the star above it. Every one of these possibilities is physically consistent with what we know. The answer is in the photons. Right now, photons reflecting from the surface of Proxima b, or from its cloud tops if it has clouds, or from its bare rock if it has no atmosphere, are crossing 4.24 light-years and arriving at Earth. They are hitting our atmosphere, some of them making it to ground level, some of them impinging on telescope mirrors in Chile and Hawaii and the Canary Islands. They carry the information we need. The atomic absorption and emission lines that would tell us what the atmosphere is made of. The spectral shape that would tell us whether water vapor is present. The subtle features that might indicate oxygen produced by photosynthesis or methane produced by life or other molecules that chemistry alone